Our next presenter is coming to us remotely. Brian Tierney is basically employed at ESnet, done a lot of work in research and engineering networks. His talk is going to be presenting recent Linux improvements that impact TCP throughputs, insights from the R&E Networks. He being a consultant, he's also being based in New Orleans, didn't have a chance to be able to come out here, unfortunately. He got his approvals pulled. And so we appreciate him being here. This is his second time presenting to us here at NANOG. His first talk was done a while ago at NANOG 64 in San Francisco, and that was based on troubleshooting network performance issues with active monitoring. Please welcome Brian back to NANOG, and it's a pleasure to have you back with us today. Thank you, Brian.
Okay. Hi, everybody. Can you hear me okay? I'm going to assume that's yes. Yep. Okay. So yes, I'm Brian Tierney, working at the moment as a consultant with the ESnet. I worked there for a number of years and then retired. This is joint work with Marcos Schwartz from R&P in Brazil. He's a PhD student down there. And a lot of this work is his, so hopefully I can represent it well. So a bit of background. Our goal was to review some recent enhancements to the Linux kernel that impact network performance, TCP performance in particular, and also their potential role on data transfer nodes. In the R&E space, we like the term data transfer node for anything that has storage and high-speed network, and it's meant to serve large data sets out to the wide area network. So in particular for this talk, we're going to focus on some new features. One's called MSG ZEROCOPY, and the other's called Big TCP. And then we also do some performance comparison with some recent Linux kernel versions. And then we're also had a combination of Intel and AMD based hosts. So we found a lot of interesting differences between the chipset and a lot of interesting differences in the kernel version as well. So MSG ZEROCOPY was a feature added to Linux back in 2017. A big part of the goal of this was to reduce CPU overhead and reduce memory copies needed between user space and kernel space for network sockets. But interestingly, even though it's been around for quite a while now, it doesn't seem like most applications use it, as far as we could tell. And I have some speculation on why that might be true. I'll get into later with some of the results. There was an earlier form of ZEROCOPY in Linux called sendfile that's been around forever. And tools like iPerf3 supported sendfile. But currently, none of the standard networking performance tools like netperf and iPerf3 and iPerf2 support it. But we did, somebody wrote a patch for iPerf3. So there's a version of iPerf3 you can download from GitHub that does support MSG ZEROCOPY, which was critically needed for our testing. The other thing that we spent some time playing with is Big TCP. This is a Linux kernel change that came out of Google. Basically how it works is GSO and GRO, that's generic send or generic receive offload techniques. They've been around for a while. And the operating system interacts with the NIC using one packet size, but then the NIC will fragment that to MTU size packets. And traditionally, the biggest piece you could pass to the NIC was 9K. But now with Big TCP, you can send up to 512K in theory. And then the NIC will still break that up into the standard MTU sizes. So it started out with v6 support with Linux 5.19, and then v4 support was added in 6.3. But there's a lot of caveats with Big TCP. It kind of requires a custom kernel build, increasing SKB buffers to work well. and it doesn't play all that well with message zero copy. You kind of want to do one or the other. And I will get into some results that demonstrate that in a bit here. So here was our test environment. Marcos had access to a test bed on AmLight, which is a R&E network that goes between Miami and Brazil. Also includes a few more sites in Georgia and Florida. And then the ESnet testbed, which I had access to, is a 200 megabit per second loop between Berkeley and Chicago. So why did we bother with two testbeds? They were pretty different. ESnet, we had AMD hosts with ConnectX-7's cards and 200 gigabit paths. AmLight, they had more latency options. Only 100 gigabit paths, and really only 80 gigs was available for R testing because there actually was some production traffic on those. And it's Intel hosts versus AMD and ConnectX-5 instead of ConnectX-7. One other thing worth mentioning, we found that network performance benefits from something called the AVX512 instruction set. Something I didn't know about a year ago, but when we started to dig into this, it's something that Intel supported first. So the older Intel chips have AVX512. AMD processors now support it, but the processes that are deployed on our testbed do not. So some of the performance differences we saw between the Intel and AMD, we believe, is due to whether the AVX512 instruction set was supported on that host. It's a little hard to prove that, but that's our belief. So quickly, just show the tuning test config we did. We're doing 100 gigabit streams across the WAN, so you definitely need to increase your TCP memory sizes. We like turning no metrics on to get more consistent test results. Otherwise, TCP caches window size and things like that from the previous test, and that might impact your results. We set everything to QDisk of fair queuing, FQ, although FQ cuddle is probably the same at this point for this type of testing. The BBR guys initially recommended FQ, so we kind of started doing that, and we kept doing it. And then the other tuning setting that turns out to be really critical for message zero copy is increasing opt-min max. And I'll go into some more details about this, but if you don't increase opt-min max, message zero copy will still save you some in CPU, but will not increase your throughput at all. We increased the ring buffer sizes on the AMD host. Interestingly, on the Intel host, that did not seem to matter. We turned off hyperthreading because that's actually quite important to get consistent results for benchmarking, and set the CPU performance governor to performance. Couple other things. Okay, we were using 9K MTUs for all these results. We disable IRQ balance. We enabled pass-through mode, IO MMU equals PT. That actually turned out to be a pretty surprisingly big difference in performance. For example, our 8-stream test went from 80 gigs to 180 gigs just by making that one change. But in collecting the results for this paper, we ended up spending a lot of time just trying to figure out how to run the same test 10 times and get something even vaguely similar. And it turned out that with this sort of testing at these speeds, you really have to be careful about what cores get used. So that's part of why you turn off hyperthreading. And so what we ended up doing is we bound the IRQ cores, which is what the driver uses, the NIC driver uses, and the application cores, we made sure that they were always separated. And of course, we made sure that all these cores are on the right NUMA node that the NIC's actually connected to. So we initially started out with just mapping everything to the right NUMA node, and just the results really varied quite a bit. So it turned out to be very important to separate the IRQs from the application. To collect all our results, we use something called the ESnet network test harness. This is publicly available code on GitHub. It allows you to run the exact same test with the exact same parameters over and over and over again. So you can convince yourself that your results are statistically meaningful. It also lets you run MPStat along with iPerf3 to collect CPU data along the way. And just to mention, I talk about pacing in the coming slides. Pacing for these tests were done using the iPerf3 FQ rate option. You can also do this, which does kernel level pacing, not application level pacing. iPerf3 also has a dash bandwidth option that does application level pacing, but that's not near as precise. You really want to be doing kernel level pacing. FQ rate option does that, or you can do it globally for your whole host using the Linux command TC. So dig into some results here, and these slides can be kind of dense, so hopefully they'll make sense. So start out, so we ran different 4 different test configurations: Linux default, Linux plus memory zero copy, Linux plus memory zero copy with pacing, and big TCP. And what we really found was that it was really easy to overwhelm your receive host, especially on the wide area network. You'd end up getting longer packet trains that would hit the receive host at the same moment, and the receive host would drop packets. So we learned that just by doing pacing, you could mitigate that quite a bit and get much more consistent results. So in the wide on the local area network, we see, and this is on the AmLight Intel host, by the way, zero copy got you a little bit better. Oh, and I should mention too, these bars at the top are the standard deviation, 1 standard deviation. So you get some sort of feel for how consistent the results were. And big TCP helped a fair amount, but it's the advantages of zero copy is pretty clear on the wide area. That's the clear winner is zero copy with pacing. Zero copy without pacing, again, it's just we got a lot more packet retransmits. So it's the combination of zero copy and pacing showed a significant increase. On ESnet, results were similar. Big TCP was not a win in this case, although a slight win on the WAN. Again, you can see really wide standard deviations until you start to use pacing. The ESnet hosts were just enough slower than the AmLight hosts that on the AmLight tests, you can see we were pacing at 50 gig, but on the ESnet test, we ended up pacing to 40 gig. That seemed to be the sweet spot where you would reduce packet retransmits and reduce standard deviation. So, this is a pretty significant increase in performance here on the WAN on ESnet to go from a little more than 20 gigs per flow to almost 40 gigs per flow by using the combination of zero copy and pacing at 40 gig. Yeah, I think I mentioned most of this. The FQ rate really helps spread out the packet train that hits the receive host. Oh yeah, by default, iPerf3 doesn't let you pace above 32 gigs, but we wrote a patch that does allow you to pace up to 40 or 50 if you were wondering about that. Now zero copy does consistently reduce CPU, and we will show some results for that here on this slide. So here is a plot of CPU utilization, sender and receiver. The green line across the top is throughput. Again, this is the Intel hosts. And you can see that on the LAN, you're your performance is limited by the receive host. But then on the WAN, it becomes limited by the send host. There's just, as your TCP buffer grows, there's more memory management that goes on the sender. So that definitely reduces or increases the CPU requirements, which ends up reducing the throughput. Now, again, when we try it with ZEROCOPY plus pacing, you can see that the CPU characteristics are quite different, right? The sender CPU is totally not an issue anymore, and you're bound by receiver CPU, and it's very consistent across the different latencies, right? Without ZEROCOPY, the CPU load goes up as the, well, I guess, yeah. Anyway, ignore that. I'll go back, I'll continue. Yeah, so on ESnet with the AMD host, it was similar but different. We're still CPU limited at the receiver, but again, by using ZEROCOPY plus pacing, we do much better performance on the wide area than we did without it. Yeah, so to summarize the CPU stuff, receiver CPU is the bottleneck on the LAN and is pretty much directly proportional to the throughput on all the tests with the default settings. And sender CPU is always the bottleneck on the wide area with higher latency paths. Now, using Message ZEROCOPY, we significantly reduce the sender CPU, and the receiver CPU is the new bottleneck on the WAN rather than the send CPU. We also did a bunch of parallel stream tests. We used 8 streams for this testing. And with 8 streams, ZEROCOPY is not really going to help your throughput all that much. It does somewhat. Although I guess on the LAN, it seemed to make a big difference. It definitely lowers your CPU, though. The other thing to notice on this slide is we tried pacing at 25 gigs, 20 gigs, and 15 gigs because the 8 parallel streams definitely step on each other. And definitely, the more streams you have, the more likely you are to overrun your receive host. And you can kind of see here that the standard deviation is pretty wide if you're pacing at 25 gigs, but once you pace it all the way down to 15 gigs, your standard deviation is much better. But of course, you have pulled back your throughput somewhat. Similar testing on AmLight showed similar results. I think I will continue to make sure I have time for everything at the end. Well, here's maybe some more details on the importance of pacing. So here we're showing the throughput, the number of retransmits, the range from the slowest in the set of 10 test to the fastest in the 10 test, and the standard deviation. And you see that you really have to pace pretty aggressively all the way down to 15 gigs per stream to get your standard deviation to be a reasonable amount. Actually, I wonder if that was 10 gigs per stream, since that's such a nice round number of 80 gigs on that one. But yeah, we're big proponents of pacing your traffic at these speeds anytime you're working with 100 gig hosts, because it's really easy to overwhelm your receiver. And wide area results are similar. You still have, even with a lot of pacing, there's still a relatively high standard deviation, but pacing definitely helped. Okay, so the other thing we did is compare the Linux 5.15 kernel, which is the default kernel on Ubuntu 22, the 6.8 kernel, which is the default on Ubuntu 24, we started this testing before Ubuntu 24 came out, so we had a bunch of results for the 6.5 kernel that we just included because we had the numbers. But let's see, so this is on the ESnet results. So just default settings out of the box, no zero copy or anything. You can see that the newer kernels are considerably faster on the LAN and less so on the WAN, interestingly. But then when you include zero copy with pacing, then the newer kernels are again pretty significant improvement. Yep. Yeah, so up to 38% improvement on the WAN, 30% on the LAN, which is pretty significant. The other thing to know that if you want to install this newer kernel on Ubuntu 22, it's super easy. They are already supporting what Ubuntu calls the HWE kernels. That's hardware something. I mean, they put out periodic HWE options as new hardware comes out, but also other new stuff comes along with that too, like in this case, a whole new kernel. So it's quite easy to play around with 6.8 if you're running anything vaguely modern. And Red Hat-based systems, it's just as easy using the L repo stuff. I mentioned BBR briefly, and interestingly, the talk from this morning about Starlink was talking about how BBR flows are very prone to stepping on each other, and we definitely saw that as well. In our environment, there was no advantage to BBR because we don't really have congestive loss. The only loss we saw was from the receive host not keeping up. And then with parallel streams, BBR without pacing was actually quite a bit worse than cubic, but BBR with pacing, then it's at least as good. But like I said, we're big proponents of pacing, and if you're using BBR, you really want to do. If you're using multi-stream BBR, you really want to do pacing. So some conclusions. So in the host benchmarking space, if you've just installed your new 100 gig or 200 gig or 400 gig persona or DTN node and want to see how fast it can go, you'll want to do all of these things, right? You'll want to make sure you do all the tuning that's recommended on the Faster Data website. You'll want to carefully separate your CPU cores from your IRQ cores. You'll want to, I suggest playing around with the iPerf 3 patched version that supports message ZEROCOPY and see what you can get. And definitely recommend using the latest, greatest kernels. I haven't talked a ton about big TCP, but in our results, it was just harder to get it to all work. It required custom kernels to make it work well and didn't play well with message ZEROCOPY. So I believe we will see more and more big TCP in the future, but I think we need to wait for at least the 6.11 kernel, and maybe that won't even quite be there yet. Google says they run it in production, and I'm sure they do, but they have custom everything, right? All their kernels are custom, so they know exactly what they're doing. Conclusions for data transfer nodes. The short conclusion is don't worry about any of this. In some ways, enough parallel streams, you don't really have to worry that much. Although we do definitely, again, say pacing is recommended so the streams don't step on each other. Your total throughput might not vary that much, but if you look at the variation, the per stream variations, it's just much better with pacing turned on. Now, for a production DTN, it can be a little tricky to figure out what's your optimal pacing. At least the worlds we're familiar with, a lot of people are starting to deploy 100 gig DTNs, but chances are the hosts they're serving up their data to are not 100 gig. They're probably 10 gig, maybe even less. So you know, you might want to take your 100 gig host and make the maximum single flow out of it 1 gig per flow. I know that may sound excessive, but if it's a DTN that often has 100 parallel streams serving 10 clients at once, and most of those are 10 gig hosts, I think you will see your overall throughput will go up and your TCP retransmits will go down. If you're just sending between 100 gig, maybe 5 to 8 gigs per flow. And as I mentioned, the TC command, oops, that was not what I meant to hit. Sorry. Not even sure how I get back now. Sorry about that. Hold on a sec. Oh, I see. Hit the wrong button. Okay. So the last thing I wanted to mention, I'm almost out of time, is I'm hoping many people in the room know about fasterdata.es.net. It's a site that I've been the main maintainer of since the late 90s. It has lots and lots of information on Linux tuning, particularly 100 gig at this point Linux tuning, more details on packet pacing, all of these things. One section of faster data that is kind of woefully out of date is our section on router tuning. ESnet now is a Nokia shop, and not very many other people are. So we don't have a lot of expertise in current Cisco, Juniper, Arista, et cetera. If there are people in the room who know tricks for any of those devices, please check out what we have and please send us updates. This work was originally presented at the Indus workshop, part of Supercomputing Conference. If you want the full paper, that's where you'll find it. If you don't trust our data, that's where you'll find it. And that's all I've got. So I'll take questions if I have any time left.
Thank you very much. Brian, we'll get some questions for sure from the room. Anybody in the room, up to the mics, please. And again, please use your name, please, and your affiliation. All right, we'll get started with some that are coming online. Go ahead, Alex.
Dan Megorian, online. Any sense of RHEL, e.g. 9.5 versus Ubuntu Debian-based results?
No, we ended up really focusing on Ubuntu because that's what we had handy. I don't think, though, it's the kernel that matters more than the release. So I don't think you're going to see much difference between Red Hat and Ubuntu and Debian. But unfortunately, that's speculation. I don't know for sure.
Okay, next online. Hunter Fuller, no affiliation. Was the iPerf 32 gig limit on pacing in there for some reason, or was it just picked as a probably high enough limitation? Seems arbitrary.
Yes, that's actually a really good question. I believe actually when iPerf first implemented it, the kernel had that limitation, that it was one of those 32-bit versus 64-bit things, and iPerf added that fairly soon after the pacing stuff showed up in the kernel. The kernel then eliminated that, and it just never got updated in iPerf 3. Now, also to be fair, your hardware has to be pretty fast. I mean, you won't really be able to pace. I mean, you have to be able to do more than 32 gigs to pace it more than 32 gigs. So it's really only the last 2 or 3 years that maybe the CPUs were fast enough for that to matter. But my memory is that when they first implemented it, it was actually a kernel limitation. It was a real hard limit.
For the floor?
Dan Curiano, Apple. Related to the iPerf question, did you upstream your changes that you had to patch to exceed that limit?
Yes, it's all sent to GitHub as a pull request.
Thank you.
Thanks,
And
Dan.
the 32 limit might even be in the current version. I'm not remembering for sure because that was a pretty small patch. To my slight frustration, the message ZEROCOPY patch is not yet in the main line. I hope they do that soon.
Okay.
One more question.
One last one from Matt Patak, unaffiliated. Great talk, Brian. Did your testing with iPerf, do you have a sense of how real-world transfer programs like rsync, SCP, etc. perform with ZEROCOPY and pacing?
Well, I could go on quite a rant about SCP and why you don't want to use that. And there's a whole page on faster data that explains why. They have their SCP, SSH, OpenSSL has its own internal buffering that really breaks things at high speeds over the WAN. So ignoring that, if you want to compare it to more generic HTTP or some of the other data transfer tools, I mean, in our world, a lot of people use Globus. I think iPerf is a good representation of memory to memory. It's just a lot of these other tools you end up including disk, so it muddies the water. Right, and sure, some of these tools will let you transfer from dev 0 to dev null, and that helps. Yeah, what I like to think of is you start with iPerf 3 as your high water mark. That's that's your best case, and iPerf 3, iPerf 2, NetPerf. I mean, I've tested them all. They're all the same to first order, especially for TCP. There's some subtle differences with the UDP.
Beautiful, beautiful. Brian, thank you so much for the data and for the information and the detailed analysis. Can we give a warm thanks to Brian, please, from the room?